Hey everyone, Mr. Skelton here, back at it. We are finishing up Unit 6 today with Lesson 11, and we're going to finish with solving equations involving natural logarithms. You may be wondering what a natural logarithm is, and so that's kind of where we're going to start. Up to this point in time, we've been dealing with logs, and if we just talk about logs, their bases, and I'm going to kind of put this in quotes, the bases can vary, right? We can have log base 2 of something. We could have log base 7. That number can change all the time. And so that's what a logarithm is, and we know that logarithms give us exponents. That's the point of logarithms. So with natural logs, okay, let's first talk about how you're going to recognize it. You're going to recognize it as ln, okay? Ln stands for natural log. And what sets natural log apart from logarithm is natural log always has the same base, and that base is always e, okay? And so natural log, when you do your homework and when you do your quizzes and tests, or if you got into a textbook, you'll never see it written as log base e. It'll just be written as ln. But you need to understand that it's always ln with a base of e. Now, what is e? Let's review e real quick. Remember that e is a number. It's like kind of like pi, right? It's an irrational number. It'll go on forever, but I'm just kind of rounding it here. But remember, e is a number, and e is a number that we used. It kind of describes a limit when we were talking about exponential growth and decay, right? We used e in this formula, and you're going to see this show up again today. But this is where we see e the most, right? And it is a number when we use our compound continuous. Remember, this is compound continuous, that word continuous, when your money is being compounded all the time. Okay? So what we're going to be doing is solving equations with natural logarithms, but before we do that, we're going to get into some of the properties. And so when you look at these three examples right here, what I want you to understand is that this is all review. Okay? All the properties that we learned with logarithms, you can do with ln. So these problems look very familiar to you. The only difference is these have ln instead of logs. So when we talk about the product property, the quotient property, and the power property, all three of those properties apply to natural logarithms as well. So honestly, you could hit pause, try these three, and all we're doing here is condensing. Okay, that's all I want you to do is condense. So see what you come up with. All right, let's jump into it. So this 5 is going to go on to the 2, and 2 to the 5th power is going to be 32. So I have ln of 32 minus the natural log of 4. Minus means divide, so I have ln of 32 over 4, which is going to be the natural log of 8. And since we're just condensing, that's all we're going to do, just the natural log of 8. Let's see if I can zoom this, get this a little bit more focused here for you. Oh, let's see here. There we go. 3 in front, using the power property, that 3 would then go on the x, so this would become ln. A plus sign means times, so I'm going to have x to the 3rd y. And so that would be condensing, or simplifying as one simple natural log. A 4th, remember, anytime you have a fraction and that fraction goes here, we're going to, in the same 1/4 goes on the x, we're going to turn these into, we're not going to leave them as rational exponents, we're going to turn them into square roots, cube roots, 4th roots, etc. So really what we get here is the natural log of the 4th root of 3 plus the natural log of the 4th root of x. Remember, the bottom number in the fraction is the index, or the root. Plus sign means times. Since they're both 4th roots, we can put these together and we get the 4th root of 3x. Okay, so what I wanted to do here, again, the purpose of these three was to show you that the properties that we did with logarithms carries over into natural logarithms. Okay? All right, let's get into some solving here. So I want to, before we do this problem, I'm going to kind of show you these problems, and you don't have to write these down. In fact, don't write them down. I just want to show you what you've already done, okay? And I'm going to show you the kind of the similarities between the two. So I have example A and example B. So example A, we have a logarithm. Well, what do you do to solve logarithms? We need to take logarithms and convert them into exponential form. We talked about this in our notes before in lesson 10. If you have a logarithmic equation, you convert into exponential form and you solve for x. What do you have when you have something given to you in exponential form? Like problem B is in exponential form. What did we do? Well, look in red, we converted that to logs. And so we use logs, and then I use change of base, and I got x equals 2. Again, you don't have to write this down. The reason I want to show you this is logarithmic form and exponential form are inverse operations of each other, or you use the inverse to solve. And that's what we're going to kind of do here. What I need you to know is that ln and e go together, all right? And so we're going to use ln and e kind of partnering in crime here to work out what we need to work out. So this is an e. We want to isolate or get this exponent. Remember, e is a number. So if e is a number, and if you look at problem B here, if you think of e as a number, it's really just like part B. So my point is if you have something given to you in e, what are you going to use to solve? You're going to use natural logs. You're going to convert that into a natural logarithm. And if you're given something in natural log, you're going to convert into exponential form. So I'll kind of show you how this works here in a second. All right, we want to solve this, so we want to isolate the 2x to the fifth. So I'm going to minus the 7.5, so I'm going to have e to the 2x over 5 equaling 9.1 minus my 7.2. That should give me 1.9. Okay, and now I'm going to natural log both sides. Now the reason I'm natural logging both sides is, remember, what's the base on natural log? It's always e, right? It's always e. So what does this become? That becomes 1. So natural log of e to e becomes 1, just like log of whatever number to itself is always 1. So I'm just left with 2x over 5. And then on this side, I basically have the natural log of 1.9. Now, in your calculator, you'll notice you have a natural log button. It's right here. I'm kind of pointing at it. We don't need to change this and do change of base and go natural log of 1.9 over natural log of e. Remember, we can just look at this as just natural log of 1.9. So I can just take my calculator and hit ln of 1.9, hit equals, and I get that decimal. Now I'm going to leave that decimal in my calculator, and that's just going to go here. What am I going to do with that? I'm going to times that decimal by 5. So times by 5, and then I'm going to divide it by 2, because I have that times by 2, so divide by 2. And I get x equals 1.60. Okay? And that's how you solve an equation when given something with e. Again, you're trying, it's an exponential form. Just think of it like we did before. It's an exponential form. You're going to use logarithms, but because it's e, we're going to use natural logarithms. Okay? So number 5 is kind of the opposite. So now you have something where it's a natural log. Well, what did we do when we had something in log form? We converted it to exponent form. We're going to do the exact same thing here. So what I always do is I'm going to go, okay, that's an e, so it's in natural log form. I need to convert this into exponent form. So this is going to be e to the 4th equals 3x plus 5 squared, right? What power on e equals 3x plus 5 squared? Now, this is a little messy here, and it's probably not the best problem. I'm not going to finish this just for the sake of time, but I'm going to kind of point you in the right direction, but I'm not going to finish the whole problem because it would take a long time. But I am going to get it down to where we need to go. So e to the 4th, right here, right above your calculator, or excuse me, right above ln button is evx. So second e, you just type in 4, hit equals. So this is essentially 54.598. And the reason I don't like this problem is because you actually have to round. Now over here, you get 3x plus 5, 3x plus 5, right? And so you have to FOIL this and get 9x squared. That's going to be 15x. That's going to be 15x, and that's going to be 25. So we get 9x squared plus 30x plus 25, and that's equal to 54.598. Now, what do you think you're going to have to do to solve this problem? Well, you're going to have to minus the 54.98 from 25, so 25 minus 54.598, and I get 0 equals 9x squared plus 30x minus 29.598. You have a quadratic. How do you solve this quadratic? Our good old friend, the quadratic formula. Okay, your a value would be 9, your b value would be 30, your c value would be a negative 29.598. And we would go x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. And I'm not going to do that because that would take too long, and I know that you know how to do the quadratic formula. Once you get your answers, you're going to want to make sure you check them, but that is how you would do that problem. That's kind of nasty. They all don't work like that. Let's move on. Last one here, number 6. It says Tyler invested $400 7 years ago in an account that is now worth $630.48. If the interest is compounded continuously, keyword there, what is his rate? What is the rate? So we're trying to find R, right? So I see this word continuously. That immediately tells me I'm going with the PERT formula. And we invested $400 7 years ago. It's now worth $630. So the 630.48 goes here. My $400 is my original investment. Remember, E is E. My rate is what I'm trying to find. T is time, 7 years ago, times 7. So we need to solve this for R. I notice the E, which tells me this is an exponent form with E. So exponent form with E means you're going to use natural logs to solve. That's the first example we did. So let's solve this up. We're going to divide by 400. So 630.48 divided by 400. So 1.5762 equals e to the r times 7. And then, I probably should have left some space here, I'm going to natural log both sides. And when I natural log both sides, remember natural log is base e always, so this makes a 1. So you basically get 7r, r7, 7r, it's the same thing. And then over on the left side, remember, I'm just going to hit my ln button, and then 1.5762. And I'm going to leave that in my calculator, but that decimal is really here, and then I'm going to divide both sides by 7. And so my R is 0.065. If that's my rate, how do we turn that into a percentage, right? We want to know the percentage. That's the decimal value, but if we go 2 spots over, that's 6.5%. All right? And so hopefully you saw a lot of similarities between this lesson and what we did in lesson 10. It's the same kind of concept. If you have logarithm equation, you're going to convert to exponents and solve. If you have exponential form, you're going to turn it into logarithms and solve. When you see e in the problem, you're going to use natural logs, and when you have natural logs, you're going to use exponents. It's a lot of the same stuff that we did in lesson 10, all right? I look forward to answering your questions in class, and we'll see you then.